Okay, so let's try number 11 in your book. So we have f of t equals the square root of t plus 3t, and the goal is to find the Laplace transform of this function. And in these problems, a preliminary integration by parts may be necessary. So our goal is to find the Laplace transform, right, of this function. So we have the square root of t plus 3t, and I'll just go ahead and just work vertically. Now we know, well, we definitely know, right, this guy, that's really just t to the 1/2, okay? We already know that. And by our linearity principle on page, let's see, so you can refer to it on page 269 of your book, right? By linearity, I'm allowed to break these terms up. So the Laplace transform of t to the 1/2 plus the Laplace transform of 3t, and we have, well, we can keep going a little bit further, so I'm going to keep the Laplace transform of t to the 1/2 plus, and I can take that 3 out according to my linearity theorem of t. Okay, so the reason we're using this linearity principle is because in, let's see, on the table, page 271, table or figure 4.14, 4.1.2, right, there's no exact f of t that looks exactly like this, right? But we can break it up into familiar functions that we know that we can find the Laplace transform of that function. So that's what I did here. And right, using linearity, I can write this, I have this, and then we know what this is, right? What is the Laplace transform of t to the 1/2? What is the Laplace transform of t? Well, according to our table, t to the 1/2. Okay, so I have a t, so again, I'm looking on page 271. I have t to the n, and I have t to the a. Now, the question is this a or is this n? Well, if it was n, okay, if n was 1/2, then the Laplace transform of that would be 1/2 factorial. But that doesn't make sense because factorials are defined only with natural numbers, right? 1/2 factorial doesn't mean anything. We know 2 factorial, 3 factorial, 4 factorial means something. So it's definitely not t to the n. This is definitely t to the a. So using the fact that this is my a, the Laplace transform of that is this gamma function. So gamma of a plus 1, well, my a is 1/2, so 1/2 plus 1 is 1.5, or just 3/2. And I'm going to divide it by, right, we need a function of s, so s to the 3/2. Okay, so that's the Laplace transform of that function, plus 3 times, well, what's the Laplace transform of t? Well, we know that's just 1 over s squared. Okay, so we have, again, the Laplace transform is, we want a function of s. So we definitely have a function of s here and of s here, but we have this gamma function, which there is a definition to it. So what is this gamma function? And if you look on page, again, so you can refer, they talk about the gamma function on page 269 of your book, example 4. And I'm just going to write some facts here so you can see them on the screen. So we know that the gamma of 1/2 is the square root of pi, okay, by definition. And we also know that the gamma of 3/2, okay, gamma of 3/2 is actually 1/2 gamma of 1/2. Okay, so I want to use this information, right, in order to find my blue part. So gamma of 3/2. Okay, so I'm continuing here. Okay, so I have gamma of 3/2, right? Here's the numerator. Well, I know that this is just this guy. So that's 1/2 gamma of 1/2. And I still have my s to the 3/2 plus, right, this guy, that's just 3 over s squared. Okay, so I want a function of s. Whoops. Oh, I definitely have a f of s, right? Or again, my Laplace transform of f of t. But I still have a gamma function here I can substitute. I have 1/2, right? But what is, again, gamma of 1/2? Well, it's right here, right? It's equal to the square root of pi. So I have the square root of pi divided by s to the 3/2 plus 3 over s squared. And you're pretty much done. I mean, I guess you can write it as square root of pi over 2s to the 3/2 plus 3 over s squared. And we'll go ahead and just leave it like this. We don't need to add the fractions. Again, you'll see why in the next section. So this is our Laplace transform of the following function, right? We break it up into pieces that we are familiar with in figure 4.1.2. So that is number 11. So hopefully that makes sense.